Hello and welcome to Aerospike Summit 2021. My name is Zohar Elkayam, and today we're going to talk about how to size, deploy, and manage an all-flash cluster. Before we begin, allow me to introduce myself. My name is Zohar Elkayam. I'm a solutions architect and a consultant at Aerospike. I have over 23 years of database experience, and I've been working at Aerospike for 3 years. Before that, I worked for 2 years as a partner. Today, I'm part of the Aerospike team in Israel. Today, we're going to talk about all-flash. We're going to talk about Aerospike architecture, what is all-flash, and when to use it. We're going to talk about how to plan for all-flash, how to deploy it, and then how to manage it, scale it, and understand common pitfalls to avoid them later. Before we begin, let's talk about Aerospike hybrid memory architectures and understand the basics. So as well as you might know, Aerospike primary index is being kept in memory while the data is being kept on a device. The data is divided into 4,096 partitions and being spread across different nodes. Each of the partitions has a unique index called a primary index, which is a red-black search tree that is called Sprigs. Each of the records is being kept in 64 bytes of memory per object. And when we want to access those records, the client will know how to identify the place where the record belongs to. It will go to that partition directly, read the location of the data in memory, and then understand where it resides on disk or in memory, and then access it and return it to the client. That entire data process is being done in a complexity of big O of 1, or in other words, one I/O operation at most. That means that if we have 10 billion objects, each of them is 1.5 kilobytes, and then replication factor of 2, then the memory utilization that we'd have would be 10 billion objects times 64 bytes times the replication factor of 2, or 1.2 terabytes of DRAM. In disk utilization, that would mean that we'd need 10 billion objects times 1,500 bytes times the replication factor 2, or 28 terabytes on data on the device, not including space that we need for defragmentation and other processes. In this example, a suitable cluster would be 9 nodes of i3N6XL, which has 1.6 terabyte of RAM and 100 terabyte of disk, and that would cost us about $150K per year. Those numbers, 10 billion objects, 1.5 kilobytes, are considered to be a good ratio of disk and memory for cloud environments and for bare metal. But what would happen if your objects were tiny? Let's say they're only 128 bytes each. Then in that place, we'll have 10 billion objects, 128 bytes per object, and replication factor of 2, meaning we'll need 1.2 terabyte of DRAM and then only 2.4 terabytes of disk. That would mean that even though we had 10 times less the disk space for data, the memory needs remain the same. And that would mean that in this example, we need 6 nodes of R5D 8 extra large, which has 1.4 terabytes of DRAM, and only reduce the amount of money that we need to spend to only about a half, to $75K per year. What Aerospike did in version 4.3 a couple of years ago is to introduce the all-flash storage option. The all-flash storage options allow the user to store the primary index in the device instead of keeping it in memory, meaning the application itself will have the same interface using the database, but instead of having the hybrid memory architecture, it will have another solution behind the scenes, which allows to keep the index on the device as well as the data on the device, thus reducing the amount of memory that we need for a cluster. That will be useful for edge system where the large number of very small objects and has a lax latency needs. In places where RAM and SSD storage spaces approaches 1-to-1 ratio, when we want to significantly save money by using this solution. There's no need to modify the data model. There's no need to build reverse lookup implementation. but it is something that might be useful for edge systems. In terms of system of records, where we keep billions and billions, many billions of records, then this cost saving can be very significant because of the reduction of the needs for memory. So, okay, so how much money does it really save us? So if you take a scenario having 50 billion objects, each of them is 128 bytes per object, then we'll need 50 billion times 64 bytes time replication factor of 2 for the primary index in hybrid memory architecture. With that will be 6 terabytes of DRAM. In terms of data, we only have 12 terabytes of data. In this example, we'll need 15 nodes of R5D, 16 extra large would have 7.5 terabytes of DRAM and would cost us about $380K USD per year. If we use all flash in this configuration, then the memory needs that we'll need for the entire cluster will be 60 gigabytes. The disk needed for index will be significant, about 16 terabytes, and we'll understand why in a minute. But the actual utilization would only be 6 terabytes like we saw in the hybrid memory architecture solution. Disk-wise, we'd still need the 12 terabytes of data because 50 bytes times 128, 50 billion times 128 bytes time replication factor of 2 is the same as before. In this case, the DRAM needs were reduced. And in this example, we only needed 5 nodes of i3N 6 extra large, which will only cost us $80K per year, which is significant. So how does it work behind the scene? So if you remember, the primary index is the balanced binary search tree, red-black tree, one per partition. So each of the partition, each of the shards that we use has its own index. In terms of how that it is implemented under the hood is that the primary index for each of the partitions has its subtrees called Sprigs that help lower the height of the tree and traverse faster and avoid locking whenever we add or modify a record. Those, when using hybrid memory architecture, are invisible for us. It's something that we usually don't need to take care of or even consider. When we want to read the data in all flash, what would happen that we would go to that specific node, we would go to that specific partition, we would read the sprig, we'll know where to find the data, then we'll load the sprig from the disk into memory, and then the record will be found there and we'll be able to read the data from the device or wherever it is being stored, without the need for keeping the entire index in memory. The one thing to understand here is that the number of sprigs that we actually need, or the number of sprigs per partition that we actually need, is something that is very important when talking about all flash and the way that we scale it and work with it. Once it's set, this number is very hard to change. That would require a cold restart, and in terms of all flash, that would need to rewrite the entire index that is stored on a device. The memory overhead of that Sprigs is pretty low and insignificant. This can be calculated with the formula that is presented right now. The one more thing to know about Sprig is that the actual size of the data wouldn't be reflected by the physical space that we see in our monitoring tools. For example, because we are allocating PI primary index differently, slowly, and more lazily, then it would look a bit weird. If we were at a hybrid memory architecture, then one object allocates 64 bytes, 10 object would just be 10 times that amount, 640 bytes. And as we go along and as we release objects and add, or delete objects and add objects, the size of the memory would stay the same, so it would be linear for that. But when we're using PI on disk, meaning all flash, the sprigs are allocated in disk allocations called blocks. Each block is defined by the operating system or the file system, and that will be 4K bytes long, regardless of how much data that's in it. Meaning that if we have one object in a sprig, then that sprig would take 4K bytes. If we have 2 objects in that sprig, it would still take 4K bytes. When we have 2 objects from 2 different sprigs, that would be 8K bytes on the device. And if you have 64 objects in a sprig, that would be exactly 496, because 64 times 64 is 496. If we had another object in that sprig, that would break into 2 blocks, and that would mean that we need to read 2 blocks of the device when we are reading the data. So once we know all of this, let's talk about how to plan for all-flash. The planning for all-flash can be a little bit more trickier. We need to plan ahead. We need to understand where we're going with the data. We need to think about the number of the projected number of objects, the average size of the object, what will be the performance peaks, both for reads and writes, and whether we are planning to expire objects or not because of full index operations that happens behind the scenes. In terms of planning steps, we'll be choosing the number of sprigs first to actually allow for the primary index to deploy completely. And then we'll need to understand how much data we would need, how much space we would need for index and data. We'll create the initial cluster size, understanding how much to allocate to index or data. And then we'll understand how the overheads for background maintenance operations affect our cluster. So in terms of calculating number of sprigs, the guideline is to try and fit no more than 64 objects into a single sprig. Meaning, if we want to have billions of objects, we need to be prepared to have multiple sprigs and no more than 64 objects per sprig. When we'll have more than 64 objects in a sprig, we would hinder performance, and we'll need 2 I/O operations just for building that sprig in memory to allocate the record before we even read it from the device. The number of sprigs is a power of 2. In order to avoid that situation where we have more than 64 objects per sprig, we would define a fill fraction, which means how much we want to fill out of the sprig before how much we want to fill out of the sprig. That's a tool. That's something that it's an imaginary number. We don't actually indicate it anywhere, but it will give us the ability to understand how full are our sprigs. In terms of what we usually do, we usually use a 50% fill fraction, or in 32 objects per sprig. But if we are talking about a append-only system or system that are not updating as much, that number can be much higher. We'll be able to add more objects to that sprig without any issues at all. So the number of sprigs formula will be the power of 2 that is closest to the number of objects that we'll need to have. So the number of objects divided by the fill fraction, and then we'll understand what will be the closest power of 2. For example, 10 billion records with a fill fraction of 50% will need 128K sprigs per partition. 50 billion would need 512K sprigs per partition. 100 billion would need 124 sprigs per partition, and so on and so forth. The number of objects that we can fit into the index would be higher than the number that we aim for because of the fill fraction. If we aim for 10 billion objects, we can actually do 14 billion objects because of the round of the power of 2. 50 billion will be actually 55 billion, 100 will be 110 billion, and so on. In terms of index size, when we actually allocate things, we'd first allocate the sprigs. Whenever we add a record, that will allocate sprigs immediately. Meaning, when we start saturating a cluster, we'll actually have objects creating sprigs created, even if there are very few records. The sprigs will be allocated very quickly, very rapidly, and then they will come to a saturation where all the sprigs were defined, but each of the sprigs have 1 or 2 objects in them. So in terms of how much space that would take on the device, we'd see the 10 billion objects will have 128K sprigs as we saw just before, and that would mean 1 gigabyte to 4 terabyte of actual index space allocated on disk. 50 billion objects will have 16 terabytes in total, and 100 billion will have 32 terabytes in total. But the trade-off here is that we don't need that memory allocated, because 100 billion objects would have needed a lot of space in memory. Once we have that, we can understand how much data we will actually have on the database and how much data we need to be prepared for. So in terms of data, we'll have the disk size, the number of objects times the object average size, time multiplication factor, divided by the high water mark for the disk. So if we have 50% high water mark, then 100 billion objects will be 4.6 terabytes, and 100 billion objects will be 47 terabytes. So 10 billion will be 4.6, 100 billion will be 47 terabytes, and that's just like we defined when we used a hybrid memory architecture. In terms of node capacity, since we divide the partitions between the different nodes altogether, then the partitions will be divided evenly, and we'll understand that the price that needs to be used for in terms of disk and index, and how much those can store in each of the nodes. That means that in order to find the optimal index size ratio, we need to balance the number of records and index at the same time. Please use the SA team in order to actually assist you with that, because there are other considerations as well when doing that. For example, what would happen when we lose a node, and how to prepare for background operations, which we'll talk about in a minute. At the end of the configuration and setups that we'll have, we usually try to account for the minimum cluster size. How much index space we would actually need on the device, how much we allocated before we actually need to completely stop the cluster in order to avoid mishaps and issues. We'll talk about this point again when we talk about pitfalls, but the minimum cluster size is essential for the configuration of the all-flash configuration inside an Aerospike cluster. Once we did that and we have those numbers, we can actually proceed to the actual preparing of the cluster. We'll be splitting the device if we are using a cloud solution, and we'll be using bare metal to use different disks if you're using bare metal, where NVMEs must be used for indexes because of the high throughput that the index is being accessed at, and in data device can be slower, but again, this is based on your performance needs. When talking about cloud solution, there's not a lot of wiggle space here. Then we'll be using the devices that are allocated by the machines. Usually when talking about AWS, we'll use the bigger one, the ones that have a lot of space, the i3ENs, for example, and then split the device between the index and the data, trying to keep those in line in order to get the maximum number of objects. In terms of memory utilization, we usually don't see an issue there. So we might use the Linux page cache for optimization, but we might not. It's really depend on the performance needs and the amount of hotness of keys inside of the cluster. Whenever we are planning the performance for all-flash consideration, it might be a little bit tricky, because read and write operations are now more than one operation, I/O operation per actual logical operation. We'll need to update the index, we'll need to update the record, we might need to update more than one sprig, and so on and so forth. We also need to take into consideration background processes like the defrag process, the nsub for explorations, and they are both heavily dependent on the index. So take into your consideration the performance needs when talking about that, and then test it before you do it, because some of the things might be noticeable and things that we need to actually take into account. In terms of write block size, it should be considered carefully to not overwork the defrag and index partition. Don't make it too big, so defragging won't have a lot of impact on the system, and usually you don't need to, because all-flash is considered best when you do smaller objects. As I said before, please use the SA team in order to actually plan for that. We have our own tools that we developed in order to do the capacity planning. So there's a lot of numbers here, but giving some of the information that we usually ask our customers, we can realize how much that would actually need, what size of the cluster we'll actually need, and what will be the alternative in terms of memory and disk allocations. We'll be able to do the capacity planning with you and understand with the fill fraction, with the high water marks, and with the disk sizes that you'll have and give us. And we'll be able to understand what will be the initial size of the cluster, what would be the alternative in terms of hybrid memory architecture, and then what would be the minimum cluster size and index stage size that would be needed for this kind of configuration. In terms of deployment and scaling the all-flash cluster, then configuration steps are pretty straightforward. The configuration itself for the namespace will be to set the index type to flash and then define the allocated mount points where we can put the files that will be the primary index. Those should be ext4 or exfs and should be mounted before Aerospike starts. The data disks are, as usual, we prefer the raw devices, so try and keep those in line as usual. We'd set the partition tree sprigs as we calculated before in our planning phases, and if the projected index size is more than 2 terabytes per node, we'll need to modify the index stage size to allow for bigger indexes per node. Another thing to consider is the fact that you might expire record from those kind of namespaces, so enabling the NSA period would be advised and would be required. And then you need to remember that that would cause a full index scan every NSA period time, and that will add for more disk utilization. So if you can avoid expiring on all flash, that would be sometimes beneficial. In terms of how the configuration actually looks like, it's really straightforward. The index type is flash, the mount points are allocated. We'll limit that to the size of the index that we want to have per node. And then we'll define the partition tree sprigs and the index stage size as mentioned before. Pitfalls to avoid would be, for example, the wrong planning for number of objects. So as we said before, in case we undershoot the number of objects when we plan, then we might need to resize the partition tree sprigs data. That would mean restart of the nodes, called restarts of the node, and rebuilding the primary index. Another thing that we often see is the wrong planning of the object size, which means that we might overshoot or undershoot the size of the data partitions. Scaling for that is pretty straightforward. You can add nodes or you can remove nodes as well, as long as you have enough index space whenever you are doing that. One thing that we saw that people are sometimes missing is the minimum cluster size configuration that is being overlooked or not being actually set. We highly recommend setting the minimum cluster size, just because that when you drop below that number, when we move partition and move indexes, index files along the cluster, that might cause some kind of disruptions. You should consider that whenever you are configuring an all-flash cluster to understand what will be the minimal size of the cluster without overshooting your index, basically because of the number of sprigs per partition. Another thing that we saw, and it's a big thing, is the disk performance that is not being scaled or not being planned ahead for high throughputs with low latencies. The basic directive for all-flash cluster is that we don't expect low latencies because of the multiple reads or writes whenever we do an operation. Background processes might also add some kind of pressure on the disk, so please allow yourself time to test it and check what would be the performance considerations for your application or your system, and how your system is affected by those background processes. Whenever we need to scale out a cluster, we need to remember one important thing. Adding node to all flash is simple and is no different from any other configuration. Adding node to a cluster would mean that we now distribute the index across more nodes in the cluster. Migration will happen automatically and the index will be created automatically. Adding nodes reduces the number of partition per node, and it's really good for scaling, but it doesn't allow us to breach without breaching the number of objects per sprig, the number of objects in the cluster. So adding node would add resources, it will add disk space, it will add DRAM, but it might not breach the number of objects that you might want to use in your cluster. If we do want to scale that, we'll need to reconsider the number of sprigs per partition. For more information, I linked here a couple of white documentation and then the FAQ that's created by our support team. Feel free to reach out to us whenever you have questions or if you need our help. The SA team is always, and the customer services team are both are at hand, and you can ask us questions. You can also go through support and ask questions about All Flash through them. I will be available for questions, but if you are seeing this late and not online, feel free to email me with questions and ideas and any comments that you might have. I wish you a very pleasant summit, and thank you very much for attending my session.
Right, thanks, thanks Zohar. So questions. So please don't be shy. Type in your questions if you have anything about All Flash and sizing and using All Flash. Otherwise, I have a couple of questions myself. Right, so if no questions from the audience. So, so Zohar, I know you've had some experience in the field with All Flash. So can you share what you've observed in terms of like performance characteristics?
Yes, even though we didn't expect the All Flash configuration to be something for that will be low latency, we did observe it to be very low latency in some cases. So the main thing that controls that is how the devices are handling the load that we are doing. And then when the service time is low enough, even 2 I/O operations or even 3 I/O operations are fairly quick and can be under 1 millisecond. So we did observe some customers running even with high loads with very low latency, like 99% when sub 1 millisecond. So,
right, thank you. Yeah, I've also, you know, have seen some. It's pretty impressive knowing that the indexes are all on disk. So let me see if any question from the audience. Not yet. So so one more. And can you run All Flash with strong consistency turned on?
Yes, it's actually one of the more preferred ways to run All Flash, because that will eliminate some of the needs for duplicate resolution when restarting a node. It's just a configuration. It's just another setting that we can do. Strong consistency is a little bit more than just a little configuration, but the All Flash is one of the settings that is just another different configuration. The same goes for having mixed loads. I know this is a question often being asked. Can we do in memory and All Flash on the same cluster, having 2 namespaces at the same time? So yes, the answer is yes, and we can run all of those configurations together because this is a mix and match. We can do more than 1 namespace at one time from different workloads.
Great, thank you. So one question. So let me read it to you. Any suggestions on how to avoid issues if the XFS file system for indices flooding up, given that it doesn't reduce itself? So monitoring on high watermark is a no-go, given that once tripped, it can't go down without cold start.
So if the question is how to reduce the XFS overload that we are seeing sometimes, and generally all the page crash and page faults that we are seeing because of the operating system, there isn't a lot to do about that. We sometimes try using different file systems, like ext4 or others in order to do that, but we did see the best performance on XFS, and we did see the best performance that we can do from that. So there's nothing much that we can do on the operating system. Like, there are things that we can do on the operating system level, but not something that we can do from the database level. I hope I understood the question right.
Yeah, I'm not sure about the second part, but that's something we can follow up. So Michael, thanks for asking, and then don't hesitate to reach out if we didn't, fully address your point. So any other questions? Going once, going twice. All right.
If there are any other questions, you can email us with the questions or reach out after that. I would be more than happy to really understand the last question and then answer that in more depth. And I'm sure support would too.
Definitely.
Okay.
All right.
I thank you very much, everybody. I really appreciate I really appreciate you being here on this session, and I hope you'll have a very good summit, because there are really good sessions after me. So enjoy that.